All right, please let me know if you can see the screen.
Yep.
Excellent, excellent. All right. So I want to start by sort of personal note on high order functions. So when I first saw this material, it was amazing to me. And as a result, this is one of my favorite topics, perhaps favorite lectures of many in this class. I was amazed. My thought was, wow, you can really do that? That is quite remarkable. And I hope you'll feel the same way after some time. So of course, Abelson and Sussman wrote Structure Interpretation, formed a course at MIT on that. Thought I'd tell you a little story is that Sussman, after revolutionizing computer science, wrote a textbook called Structure and Interpretation of Classical Physics, where he did the same thing. He reinvented all of physics within functional context and also proved that the solar system was unstable after a sabbatical at Caltech. And Sussman's hero, and he would say this, I knew him quite well, he's still alive and doing research. His hero was Richard Feynman. And Feynman's hero was Einstein, so there's sort of a chain there. And if you like to think about it, in some sense, my hero was Sussman. So there's a chain going along here, and certainly as we, in the beginning of the chain, there's some drop in intellectual firepower, but not at the end. But what Feynman is famous for these days is mostly nanotechnology, although he essentially won 2 Nobel Prizes for other things, quantum chromodynamics. But what he used to say is, what I cannot create, I do not understand. And so the approach we're taking to computer science and mathematics is trying to build these mathematical and computational objects with our hands, so to speak, and our other tools so that we can really understand them. And I think that as far as what we're doing today, we're actually going to build some mathematics, build some computer science using our tools in order to, by creating them, we can understand them better. And we're going to do a lot today, actually. I put up some puzzles if you came early that we're going to, that will just feed into what we're doing. But let me mention that we're going to do all sorts of things. And we don't need for this lecture any additional syntax, no new special forms, no new primitive functions, no anything. We're just using what you already know, combining it in new ways. And this is one of the powers of this minimalist lambda calculus approach, is that to do something super powerful, we might not need any new constructs for this. So there's sort of a setup, a kind of personal statement, if you will. I mentioned that the main topic is higher order functions. And there's some really good reading in SICP. So I mentioned start on problem set 2 now, comment on the pace of the class. Yes, the course is fast paced. It's designed for Duke students. I've been told by my colleagues at Carolina that they couldn't give this to their students, just the top ones, but you all do really well at it. So the pace is fast, but it does not get faster, unlike some classes. We don't want to accelerate. And for all the problem sets, now that you can have partners on your problem sets, please take a look at the integrity matrices that we provided to see what you can share and what you can't. Okay, so moving along, let you read some of that. The main things I want to talk about today are higher order procedures. So functions as arguments to other functions and functions as results of other functions. And the reason we gave you problem set 1 is so you'd be motivated to learn more about this. It's a little abstract if you haven't tried to do it yourself. So can you have functions as arguments to functions? Can you return them? So this is actually a programming paradigm. It's really a technique for managing complex programming problems, which I think is, pretty cool. It's also used in just constructive mathematics. So this is where we build mathematical objects for modeling functions. It's really different. It's very cool. We're going to see if you can really grok functions today. Basically, this is pretty mind-bending what we're doing today. But it's a great topic. And the mantra for today, which you can say whenever you wake up, is that procedures are just like any other value in scheme. They have all the rights and privileges of anything else. You can treat them as just if they're an integer. You can pass them around, return them, put them in data structures, and so forth. So to motivate this, really what we're talking about today is a technique for abstraction. We want to capture, what do we do in abstraction? You've seen this, of course. We want to capture a pattern of doing things and package up so we can use it later, use well. So more precisely, we make a procedure that captures the common parts, and they stay fixed, and we pass in the differences as parameters. And this is the basis of procedural abstraction, although we don't usually, unfortunately, confess that to students. But that's really what's going on. And so we saw lots of things like taking times 3, 3 and times 4, 4, which, and so forth, and writing an abstraction of that, namely the square function that does this. And the square function, again, to, start out slow, it takes a number and it puts it into this box called square. And that outputs a number, which is what we want. And basically the what is description of that, this is the procedural description, is basically saying that, square x is equal to x squared. Again, the equivalence of a scheme expression and a mathematical expression, which is what we want. And in some sense, this together captures the notion of squaring, or the process of squaring. So now I want to take this one step forward, and I want to show you some mathematical objects you may have seen, but actually they can be coded up really nicely using high order functions, and much better than some kind of iterative loop or something. So if you think about this summation operator, or sigma in some sense, this is an operator, it's a function that is going to take it, it's a function that takes a function as inputs, right? So think about what we have here. I'll sort of draw this out. If we think of mathematics, or sigma as a function in a box, what does this do? It takes as input a function, and it takes two numbers, and it outputs a number. So you already know a lot about higher order functions because you've seen things like this. So this is pretty nice. Now, an example of this would be right above here, where we do a particular summation, which I'll write out. So let's take a summation like this. We'll take summation for I equals 1 to n of I squared. So this sort of reifies the abstract diagram I have below. Sigma takes in a function, namely the square function in some sense, and it takes in two numbers, an upper and lower bound, and this then returns a number. By the way, does anyone know in closed form or any other characterization what this equals? What does this summation equal? Any ideas? Andy, did you just tell them the answer? I'm a little confused.
I think there is multiple Andrews in the class.
Oh, there are multiple Andrews. That's great. So was that Andrew Zhang, the head TA, or was that Andrew Zhang, student in the class?
I'm the student in the class.
All right, it's nice to meet you. You got it right. That was very good. So I don't. We'll have to find a way to because I talked to Andy a lot, so we'll find a way to discriminate. But thank you. All right, so your answer was correct. This is equal to n times. Oops, didn't mean to move that around. Let's do it over here. I'll write it over here instead. This is equal to. Why did it make that move? It's equal to n. Let's see if we can get far enough away. N times n plus 1 times 2n plus 1 over 6. So that's what this is equal. So let's just think about that for a minute. I want you first to notice that this has order of growth n squared because it's got an n times 2n in there, so it grows pretty rapidly. But second, if we wanted to know this was true, we could prove this. This is a very nice induction proof. And you can prove this using induction. And one kind of bonus is you don't need the substitution model. You just use mathematics for that. So I'm going to leave that as an exercise for you all to do. And you can talk to us about it. We'll give you hints. That's a great thing to warm up on. All right. So this sigma function saves a lot of work, right? It saves work in programming as well. And let's try to capture that a little bit here. Let's think about this. So for example, suppose we had, let's put a little more light on the subject. Suppose we want a program here that's going to sum up just the integers without squaring them. So I'll write this again using my notation, sum from I equals. Now I'm going to generalize this and have a possibly different upper and lower bound, so I don't have to start at 1. right? So it's going to sum up the integers starting at I. Here, the magic of erasing. So this just sums up the integers starting at A and going to B. And I've written that here as a simple recursive procedure. So I take in integers A and B, and I have the summation here. I haven't really captured, a high order function, but this is a simple recursive call. So some things for you to think about. This is a recursive procedure, and it generates a recursive process. It's kind of just like our times one. So what you should be asking yourself is, can you write a tail recursive version? Can you prove that this code above is correct? Can you prove that the code for tail recursive version is correct? And let me mention that I'm asking you new problems, but we don't need any new machinery. You have all the tools to do that now, which is kind of cool. All right, so these are questions for you to consider. We might do some in recitation. Let's look at some related code here. So here's kind of what we had before. Here's a function that sums up the squares of the integers. It's just the same as we had before in mathematics, but we're going to start at an arbitrary lower bound A. So I'll write this as the sum for I equals A to B of I squared. And here, the closed form isn't quite so obvious. Thanks to Andrew for giving it to us in the case of 1. So now we have a procedure to sum up the integers and a procedure to sum up the integers squared, starting at arbitrary upper and lower bounds. So these two procedures share a lot of structure, and in fact, they look nearly identical. You're just summing up different things. So the only real difference here in the procedure is whether or not you're summing up the square, A or the square of A. So here we're summing, basically calling square of A here, and let's use a different color. And here we're summing A instead. And of course, because they have to call themselves, this part differs as well, but that's not an interesting difference, right? It has to call itself. So really the only difference is in what you're summing in some sense. So here's where abstraction comes in, and high order procedures will be, pretty cool. What we're going to try to do instead is we're going to try to make a procedure that abstracts away from these differences. So what we're going to try to do is we're going to pass in the differences as parameters, and we'll of course have the general ability to sum between arbitrary integers, our numbers, not just integers. So basically we have the ability to go to start at A instead of 1, which is we already have here. But also we're going to make another generalization so we don't have to go in steps of 1. We had a question about this yesterday, last Monday, that I thought was really good. Do you always have to step by 1? In fact, sometimes you want to step by other things. Might not even be integers, might be different kinds of things. So I'm going to abstract away from sum int and sum squares, right, to write a general procedure that's more like our beast here, which is the summation function. So in other words, it's going to be something like this mathematically. It's going to be something like a function sigma. It's not going to be called sigma in scheme. It's called sum. It takes in a function as input, and the upper and lower bounds gives you back a number. All right. Everyone see where I'm going with this? Maybe not how to do it, but the motivation? Good, good. I mean, I see people are willing to give me some rope. So here's my procedure that's going to do the summation for me. So look what I have here. I'll sort of draw attention to this. So what I have in this case, I take in as before A and B, the upper and lower bounds, and I take in a function, which is the thing to sum. So that would be like the identity function, or it'll be square or something else. And I'll take in a new thing, which is a step that tells me how to step between different things. Like, do I just step in terms of 1, or do I step in steps of 2 or 3 or something else? It could be arbitrary, it doesn't even have to be an integer. And same structure as before. Unless I've exceeded the upper bound here, what I do is this. So notice this simple syntax. Thing to sum is a function. So how do I use it in the procedure? All I do is you put it in the first position of a combination. So the function that I'm summing up, thing to sum, gets passed in, applied to A, then that gets added to a recursive call to sum, where I've stepped A forward using the step function. So step is the thing that takes your current index and increments it, perhaps not just by 1, and thing to sum is a function like square. All right, so a little bit strange to think about this, but let's try to do it. And let's look at an example here. So the simplest way to think about this example is I first have to just tell you, how do we increment? And here's a simple function that does this. 1 plus is going to basically add 1 to an integer. So 1 plus applied to 10 will give me 11. 1 plus applied to 100 will give me 101, and so forth. And so what I want to do here is I want to try this simple example above this, sum applied to 1, 2, square, and 1 plus, where 1 plus is defined like this. So what I want to be computing here mathematically is 1 squared plus 2 squared, and that better equal 5. All right. And so notice what I've done here. The in this call, 1 and 2 are a and b, the upper and lower bounds. I pass in the function, which is the thing that I'm trying to square, basically, and I pass in the iterator, if you will, the thing that increments to the next step. And I've done this because I want to be able to pass in different functions: cube, square root, Bessel function, some weird other thing, parabola. And I want to be able to step along in different steps, not just steps of one. Now, in order to verify that this is in fact what it computes, what would we use? The substitution model, of course. Now, this is relatively straightforward. I'm just going to show you the evaluation steps of the substitution model, somewhat simplified, but you can work the whole thing out yourself, and this would be a good exercise to do. So let's just go through it a little bit. So what we're going to do here is we're going to start by calling sum on 1, 2, square, and 1 plus. And let's go back and look at the code here. Looking at the code for some squares, sum. Now, I think it would be more convenient here if I were to maybe get rid of some of these things. So I'll throw these out. So we've called sum down here with 1, 2, square, and 1 plus. That's fine. And we don't have the base case yet because A is less than B, namely A is 1 and B is 2. So now we're going to expand the body and do some substitution. And that comes out over here. So if you look at this body here, basically, again, substitution model is aptly named. Here I have thing to sum applied to A. That changes to square applied to 1, right? Because A evaluates to 1. And thing to sum evaluates to square. There should be a procedure there, but this shows you the basic idea. So what I've done here is expanded out this first step. I have plus square 1, and then a recursive call, which is also indicated here, to sum applied to what? To 2 and 2, why 2? Because I've incremented A by calling 1 plus. So here we have the square, here we have the recursive call. At the next level, that expands to the following thing. I have my stacked up deferred operation for square 1. Then I have a new deferred operation here, square 2. Why? Because thing to sum here, which is square, is applied to A, which is now 2. I have the square A. Then I have a recursive call, why 3, 2, because I applied 1 plus to 2, I've gotten 3. Sum applied to 3, 2, I have to pass in square and 1 plus. That's my next call. This then activates the if statement, and I return 0 with the next call. So I have plus square of 1 plus square of 2 and 0. And of course, this is going to work out to 1 squared plus 2 squared equals 5. Why? Because 1 squared is 1, 2 squared is 4, plus 4, and 0 is 4. And I get 5 as desired. All right, so a simple example, and you can validate all of this by substitution model. Now, there's one remaining thing that we have to do here, which is we have to actually define some squares, right? We have this thing, we haven't actually quite done that. But so to put that in, we just go like this. Remember, sum squares before was this big mess over here, right? That looked exactly like sum int, right? So it's this thing here, it's got squares in here, it refers to itself and so forth. And now we can generalize that as follows. And sum squares becomes this beautiful piece of code here. Basically, again, think of this as I take my sum function, I put in a function, which in this case is the square function. I put in A, the lower bound, I put in B, and I put in this new thing, which is the iterator, which tells you how to step along. And this returns a number. So I've almost exactly matched the mathematical definition of sigma, the summation function, because sum squares is basically just a call to sum, which is sigma, lower bound A, upper bound B, the square function, and the 1 plus function, which just takes any number and adds 1 to it. Okay. So that's an example of a higher order procedure, namely a procedure that takes a procedure as an argument, and how it can simplify how you think about mathematical issues and probably computer science issues as well. Now, what I'd like to do next is sort of use our tools to do more and do a little calculus, actually. So I want to do an example using this function because things like summing come up in calculus a little bit. So let's just start out with a little puzzle to think about who remembers or who can work out what this integral is equal to. Does anyone know? I'm not expecting everyone to know. This is the kind of thing you would remember if you took Calculus BC recently and remembered how to do it, or you took
The
engineering.
arctangent?
It is arctangent, but you're exactly right. It'd be arctangent, but applied to what argument? So let's put this.
Of A, right?
Yep. Okay. So exactly right. So that's perfect. So this is equal to arctangent. So very good. So we're going to use that fact later. So the integral of 1 over 1 plus x squared from 0 to a. That's why I call it a definite integral, a numeric. You know, we're going to could be this numerically. 1 to a, that's equal to arctangent. So remember that. We're going to come back to that and do a little example here. Okay. So I said we do some integrals. Let's think about that. So it's going to be approximation, of course. So recall that if we have an integral we want to do here, you know, the integral of a function f from a to b is approximately f of a plus f of a plus delta x plus f all the way up to f of b in steps of delta x times the quantity delta x. Now, of course, as a mathematician, we know that the integration is only exact, only converges in the limit, and in fact, only the limit will really work. But this is quite a good approximation to the integral when delta x is small. And you might wonder why I don't have a dx over here. I mean, the concept of a integral is actually defined independent of the coordinates, and often mathematicians just write an integral like this. But we'll use some dx's later. So this delta x is a finite approximation. We're not passing in infinitesimals. This is the standard approximation or Riemann sum that you might have seen in calculus or in engineering. So this is a sum where we step along in steps of delta x. And it goes from a to b, and we're effing all of those quantities. So why not use our sum procedure to do this? And here I've done this here. So this is the integral function written below. It takes in f function. It takes in a and b, the upper and lower bounds shown here, and it takes in dx as a number, because this will be an approximation. And what we do here, we put the times dx on the outside over here, and then we just call our sum function. What do we call it on? Well, obviously a, b, and f, because the sum function takes a lower bound and upper bound, and a function f, and it's going to f all its intermediate values and sum them up. But what about the step function to get to the next thing? What I've done here is I created an anonymous procedure, a procedure that takes its argument and increments it by dx. Now I feel stylistically there's no point in giving it a name. It's a throwaway. You're never going to use it again. We could have named it, use letrec, use let if we wanted to. There's no real point. So here's the mantra in real languages like Scheme. Not every value needs a name. The same as procedures, because procedures are just another form of value. But yeah, if you wanted to experiment with making an auxiliary function, hopefully you'd make it internal using let or letrec to make it so it's not exposed outside, but this just steps along. And
good question.
Yes.
So it's not possible to use the define inside here again. You can't use define twice, like define integral, and then you say define something lambda.
Yeah, I understand what you're saying. That is actually allowed, but we deprecate that in this class. And the reason is we want to separate out the creation of procedures from their definitions. So in this class, internal defines are deprecated and we use let or letrec instead. But you're absolutely right. It could be done that way. It just isn't as elegant, and it kind of is confusing to have the nested defines. Because to read them, you have to understand the level of nesting. Good? Did I answer your question?
What's the difference between, oh, sorry.
Go ahead.
So in regards to like letrec versus let, like, so what's the difference between the two then?
This was covered in last lecture, so I'm going to refer you to the notes.
Yeah.
But letrec is
Okay.
used when the procedure, well, but I'll tell you briefly, letrec is used when the procedure you're defining needs to call itself because it's not defined at compile time. In this case, the procedure doesn't, so you could use let, but either would work.
Okay.
So what I would say is take a look at those notes. If that's not clear, contact me out of band or after class, and I'll happy to. Yeah.
Okay.
But you don't need to is the point. It doesn't need a name, right? Okay. Great questions, by the way. All right, so we're going to use that at this point. Let's just remember our, you know, a little arctangent here. I'll just write this out in mathematics. So arctan so this mathematically. So scheme has a very nice arctan function already. In fact, it's the two argument arctan, which lets you discriminate between quadrants, sometimes called atan2 in other mathematical languages. So you don't actually need to add this function. But if you wanted to add it, you could do it this way. Namely, I would just code this up, this mathematics up, by calling integral. So remember what integral was here. Integral did our integral for us. I define arctan as follows. The only argument is a, just as your colleague said, which is the argument here. And now I compute the integral. And let's look at the last part first. From 0 to a in steps of 0.01. That's pretty cool that we can do that. And then I don't need to name this weird function in the middle. Like, why would I care about that? You could name it. Instead, I make an anonymous procedure without a name. And this is just encoding dividing 1 by 1 plus the square of x. So this here just encodes this function there. And now I have an arctan function, I can use it. All right. So the key point here is that we have procedures that take procedures as arguments. And these are really control structures, right? They're ways of packaging up the flow of information and the flow of instructions here. So what we've done is we've abstracted away or packaged up the concept of adding up a bunch of stuff into a function. We can use them as tools and we can build really quite sophisticated math in CS very rapidly. That's the real beauty of this from a programmer's point of view, which is kind of a nice thing. All right, and we can use this. Let's see now. I wanted to mention, yeah, so that's really the points I wanted to make about this. So this is about taking functions as input and returning numbers in some sense. And we're going to move on to something a little more complicated, which is functions that return functions. But I'll pause and ask if there are any questions on doing this. So basically we've written code to instantiate the mathematical summation, or sigma. Everyone calls it summation in math. And we've generalized that code to actually do numerical integration. And then we've used that to package up an arctangent function because we knew what the integral would be. So we can layer these things up pretty quickly. All right, any questions about these examples of using higher order procedures in order to do a little bit of calculus and layer things together and abstract away the notion of summation?
We have a raised hand. Michaela, you can just unmute yourself.
Oh, thank you. So I have a question that may be a little bit of a tangent, but the process returned is going to be a recursive process for sum. Is there a I don't know how to like word the question, but is there like an easy way to tell if it would be possible to turn that into something tail recursive to make it take up a constant space?
You've asked a very good question. So yes, this could be made tail recursive, and that would be an excellent exercise, one we might give you or one you could practice with. So I think that would be a fantastic thing to do. And it would be similar to things that you're already doing or have seen. And that would be great. The question of when you can look in general is, well, from a programmer's point of view, it's a matter of kind of recognizing when you can. Being able to look at a procedure and decide whether or not it can be written as a tail recursive process, there are certain barriers to knowing that, although you can decide it in many cases. And that's because it's a property that's difficult to deduce from complicated programs. And there are processes that are recursive that cannot be made tail recursive. And these are, so to speak, the most difficult recursive functions. We probably won't see any of those in this class. So probably, in general, it's worth trying to see if you can make them tail recursive. And when you take a structural complexity class later in your career, you can see that there are functions that are recursive that cannot be written tail recursively, and what are the barriers to knowing or proving that. So a great question, but the things we'll see here largely can be done in a tail recursive fashion. And I'm happy to discuss this more with you offline, like after class or another time. It's a great topic, but a little bit beyond where we'll be getting in this class.
Okay, thank you. Yeah, I have another question, but we can do it after class.
Sure, absolutely happy to do that. Okay. All right, so what do we have so far? We have seen this is basically passing functions as arguments, but what about returning functions as values of functions? So this is, I'm going to give a trivial example, a trivial in the sense that it has no mathematical interest really, but then try to do something interesting with it. This is generally harder. So don't beat yourself up if you don't get it. Take some study. We're going to help you with it. But the main thing is you don't need any other tools. Substitution model does all of this for you. So there's nothing new being introduced. It's just the rules you had before being applied to this problem. But extremely possible because it lets us do actually the rest of calculus. Okay. So let's look at this weird beast here called add n. So what type is add n? Well, obviously it's a procedure because the outer lambda is going to return a thing of type procedure, but then gets bound to add n. That's good. But what does add n do when it gets called? Well, it's going to call lambda again on the fly, which is going to make a procedure and then return it. That's the reason this thing returns a procedure. And this can be thought of as a sort of paradigm for simple procedures that return other procedures. If you see that, it's kind of an idiom for a function that returns another function. So remember, the outer lambda is evaluated to define time. Lambda always returns an object of type procedure. Define then binds that to add n. When you call add n, and we'll simulate that in a minute, what happens at that point is that the inner lambda gets called on the fly, and it can only be on the fly because only at that time is x defined. At that point, it creates a procedure, and then that's the last value, so it's returned. So this is a procedure that returns a procedure. It always looks like this. That's what the value looks like. So let's take an example here. So let's suppose we call this with argument 2 like this. So this is going to, the value of this is going to be a procedure that adds 2 to its argument. So let's just work it out in terms of the substitution model. If we call add n with 2, as I've done below, what happens is the inner lambda gets evaluated, right? Because how do we do this? Just substitution model. And we're going to have plus x n as our formed. And of course, we're calling this lambda x. So this is the key form that's getting evaluated when we call this with 2. So when we apply this with 2, we now have to do the substitution model, which I think of as erasing. So what we're going to do here is we're going to replace, i.e. substitute a 2 for the n like this. And then this thing returns this procedure object here, which I'll just write down as, I'll write the same thing down, proc x plus x2. And this is, again, just the same notation as here, one typed, one written. So the key thing is if you ever get confused by these things, just use the substitution model and it'll always tell you what's going on. But you have to get good at the substitution model so that you can do this. All right, so this then returns a procedure that adds 2 to its argument, and we can use it like this. Obviously, this is a procedure. We can capture it like this. So remember, this thing here returns that procedure object. This then binds that to add 2, which we can use just like any other function. What is add 2? It's just a type function. And here we do it. Let's just do the substitution model here. If we say add 2 applied to 10, well, that's pretty cool. What is this going to look like? I have this procedure object over here. I have proc, write it again, x plus x2. Remember, that's a procedure object that's been evaluated. That's applied to the value 10. We're at the apply stage of the evaluation rule. So I instantiate the body. What's that? Plus x2. I want to evaluate this. That's fine. Now, I now have applied that. I'm applying this to 10. So what I have to do here is I have to replace the x by my 10, which returns 12 as desired. So now we can make a procedure and we can return it as part of to return it as a value. So the key thing to remember here is that in some sense, procedures aren't special in Scheme and other decent languages. They're just like any other value. Okay. So given what I understand some of y'all's backgrounds to be, I have this heuristic to kind of help think about this a little bit. And maybe you'll find it useful. So it's not a perfect analogy. Let's see if you like it. So you know about objects, object orientation. You've seen them in Java or Python or something, maybe. You've at least heard about object orientation, maybe. So with objects, you got to make them. You might have make vector, make window, make spaceship, make matrix, make something else. So a procedure is just a kind of object. And you could basically think without a lot of, not losing much generality, as lambda as being a Greek name for make procedure. Lambda, i.e. make procedure, creates a procedure and returns the proc object as its value. And that's really how to think of lambda. But why would you ever want to do a thing like this? I mean, why is this valuable? Well, one example is the other branch of calculus, other half of it, which is derivatives. And in fact, you've already seen this. So the main point here is that higher order functions are things you've already seen. You just maybe didn't have good tools to compute them. And Scheme and other functional languages give you that. So let's look at derivative. Like derivatives, you could think of as a big operator, which I'll call D. And if you apply the derivative operator to the function x cubed, you get 3x squared. Right, that's pretty familiar territory here. So D is this operation here. And what it's going to do is it's going to take, D is an operation. It's just like, it takes a function like x cubed and returns another one like 3x squared. So we have our same picture as before. We have this D box for differentiation. We're going to take a function as input, and we're going to return a function. Now notice this is really different from numerical integration, and I don't mean that by just saying it's the opposite in some sense. Really, it's only the opposite for indefinite integrals. But when we did numerical integration, because I wanted to bring you up in this in a graceful and slow way, there we had the numerical integral returning a number. But here we have the derivative returning an actual function, which is somewhat more interesting. So we take in a function like x cubed, and we return a function like 3x squared. And of course, the functions will be Scheme functions, so we can actually get at them and analyze them. So how do we do that? Well, just recall we can approximate a derivative as follows. I've written it down here. Let's just do it. So the derivative of some function, say x squared, can be approximated for small dx as f of x plus delta x minus f of x quantity over delta x. And for small delta x's, this works quite well. So what we can do here is we can actually use this to compute derivatives. And here's my derivative function here. So same kind of setup as we had before. I'm going to scale up. I hope I don't make you dizzy or seasick. Now, to really work this out, you need to use substitution model. But notice the idiom. If I have nested lambdas like this, it tells you that this is going to be a procedure that returns a procedure, because that's all it can do. The first lambda defines the procedure that's being bound to add n. The second lambda tells you that's what's going to be invoked when you call add n, and you're going to return an object of type procedure. Similarly here, this tells you by the idiom here that of course deriv is a procedure, but when you call deriv with the proper arguments and it terminates, it's going to return a new function. So all I've done here is I've slavishly coded up what I had before, namely the derivative function. I've just coded this up here. So look what I've done here. I've said, okay, deriv is going to be a function of two things, f and a dx, which is my approximation of dx, some small number. And what I'm going to do here is I'm going to return a function, and that's exactly this beast here. Now, how do I do that? I just code up the algebra here. So look, at the end, I'm going to divide by dx. That's this part here. And here's the part where I difference f of x plus delta x and f of x. So this returns this function here as my derivative. So calling deriv with f and dx returns another procedure, and we can try it here. I've already shown you the answer, so I won't ask you this question. So if we take the cube function and apply deriv to it, remember this is going to return a function that's kind of like 3x squared. That's what this should return. And we evaluate that at 0.5, we're going to get something that ideally should be 75. Now, I'm just going to let you read this. Do you understand why it's not exactly 0.75? Why that might be? What do you think? Have you ever encountered a numerical approximation that wasn't spot on like this before? Yeah, so Riyadh has it right. This is because of the approximation. So basically, this is a good approximation when delta x is small, but there'll be a small error. It's not exact until you take the limit. So you can expect that if you put in a smaller delta x, that the error in the approximation is going to go down, never completely go away, so you take the limit. But still, it's a decent numerical approximation to a derivative. Okay. So again, deriv is a procedure that takes a procedure as input, or in mathematics, it's a function that takes a function as input, and it returns another function, which is what we want. And in this case, it differentiates the function, so it takes x cubed as its input, and it returns a function that's very much like 3x squared, done by numerical approximation here, as its output. And then you can apply that to other things. Notice how I applied this here. So if we look at this beast here, when we apply this thing, we apply it by simply putting it in the beginning of a combination. And then it's applied to the remaining arguments, namely just 5. Okay. All right, any questions on our glimpse at higher order procedures that return functions as their values? And in particular, any comments on implementing derivatives in Scheme? All right, let's do a couple more things. I'll give you some things to think about, another exercise to think about. So the first exercise is to prove the induction that Andrew Zhang pointed out. Namely, we know the answer, but how can we prove that using induction? Another one is this problem here. Okay. So in summary, deriv returns a procedure. And so to use it, you just put it in the first position of a combination. So just to recap that, deriv the cube function and 0.001, this returns a thing of type procedure. So to use it and apply it to 5, we just put it inside parentheses like this, and we follow the rule, the procedure will get applied to the arguments here. Okay. We have a great course taught by Xiaobai, who's amazing, and great teacher, talks about numerical methods in computer science. I highly advocate that course as you go on in your CS career. So there are many other things you could do with high order procedures. Here's one that is extremely useful, which I call repeated. So mathematically, you sometimes have a function of say x or whatever, and you'd like to do it many times. So you get an you get a value x, and you have a function f. You don't want to f it once, you might want to f it 2 times or 4 times. You might want to f it a lot of times. So we have repeated that will let you do that. So mathematically, I have this written down, we might have a function and we might want to apply f to it multiple times. Where the number of f's is n times. So n is sort of going to be a parameter here, and we're going to take x and we're going to f it n times. So this would be the repeated function. So the idea is that this should be the mathematical value of repeated. What does repeated take? F and n. So this returns a thing of type procedure, and then we apply that to x like this. So this is a great exercise. By the way, if you get stuck on these exercises, talk to us. We'll give you hints, and I will eventually reveal the answers. I'll probably put them up as notes or something, but try them yourself. See if you can write this. Again, it has the same idiom. The nested lambdas, the second lambda, indicating that you're going to return an object of type procedure. So let's look at how we would do this, very computer science example. Suppose we take the square function here, and we apply repeated to it in 3. So repeated square 3, this is the same as square of x, i.e. do square 3 times, or the 8th power. So in this sense, as an example, if I take repeated square 3, or the 8th power, and apply that to 2, I get 256. So the function returned by repeated fn is going to be a function that takes a value x and it f's it n times, or applies f to it n times repeatedly. Questions? I saw a question in the chat, but I'm not sure it flew by pretty quickly because I'm sharing my screen. N will always be an integer in this case. This is a very interesting mathematical question. Abe already answered this question. So it relates to actually a deep question in physics. So, you know, if you think of acceleration, so you have some, you know, F equals ma, right? And in physics, this is mass times the position differentiated twice. Where you use the double dots. Double dots is equal to the second derivative of x with respect to time. We'll pretend to be physicists for a minute. And we'll pretend to write neatly because we're physicists. All right. So one thing you want to know about Newton's laws and actually all physics is that it's a model, right? You think it's how physics works, but it is only accurate because it describes experiments well, right? Well, one thing you might ask is, well, why is it second derivative? Why isn't it third derivative? Why isn't it first derivative? I mean, before Galileo, everyone thought that it was just m times v, right? A pre-Galilean world because you had drag on things. But that's a very interesting question. And in fact, if you've taken some engineering classes, you know that there are systems involving magnetism where actually the system is third order, not second order. But the really interesting question that relates to this question of does n have to be an integer, because you see that this is two differentiations. That's why this could be repeated differentiation here. Why is it an integer? And in fact, you can define fractional derivatives as well. And it's kind of a mystery why they don't actually occur very much in physics. So if you are careful about it, you can define what it means to take the 2.5th derivative, or the 4.7th derivative, or the pith derivative of a function. They have mathematical applications, no known physical applications at the moment, to my knowledge. But it's kind of remarkable that it's fixed in integers. Why would nature do that? But in this case, it will always be an integer, mostly because I declared it to be, but also because it's not really clear what it means to have fractional application unless you go on to some more complicated mathematics. So great question. Always want to try to generalize those things. So I'm going to move to the document camera, do some stuff in a minute to continue. But the main point of this is that in Scheme, procedures are what we call first-class objects. That's the computer science term for it. So they have all the rights and all the privileges of any other values. You can pass them in as arguments. You can return them as a value. You can name them with a variable, and you can even store procedures and data structures. And we've seen all of those except the last one so far. And maybe we'll see the last one a little bit later. So I've left some time for questions at the end. I think we still have that time, but what I'd like to do is I want to show you a little more about how this fits in to our view of, discrete mathematics and mathematics in general. So we've done a lot today, but what I'd like to do is switch over to the document camera. We'll have dead air for a minute. You probably wondered why I was so intent to show you the Three Stooges before. I want to show you some videos later, and I wanted to see if videos would play over Zoom. Three Stooges seem as good as anything, especially in our current climate. I think the videos were a little bit jerky looking at the recording, and so we want to find a different way to show you videos. Obviously, you can click on them and view them. So that was an experiment that we tried to do. But if it's popular, we could have cartoon interludes while I switch devices. So feel free to rest for a minute. I should be back in 30 seconds with the document camera and do a little bit more. All right, please let me know if you can see the paper and if you can hear me.
I can see it and hear you.
Excellent. Okay, fantastic. All right, let's do a little bit more. I want to kind of put this in context and convince you that this is something that is a powerful tool in mathematics that you may have thought about. We can do a lot of different things with it. All right, so we started out with, some little calculations to get us warmed up. Thanks to Andrew, we now know this is equal to n times n plus 1 times 2n plus 1 over 6. And your task is prove by induction. And also thanks to, I believe, was it Moses? This is equal to arctan which is great. And you can prove that, but you don't need to prove it right now. So let's look back again at this case here, our case of our arctan and our integral. And I want to mention to you, just so it's familiar, that what we're doing in this case with respect to the integral function, either the mathematical integral function or respect to the scheme integral function, is that we're fixing some input parameters to the integral function and allowing others to vary, right? So in this case here, we're fixing f, the function, which is this 1 over 1 plus x squared. We're fixing 0, and we're fixing dx. That wouldn't happen in math, but we're fixing that in some sense. And we're varying a. And this is a very common thing in mathematics. It's also very common in computer science. And this process is sometimes called currying. So we're going to wall this off. This has nothing to do with currying. Sometimes called currying. And it's named after the great mathematician, a colleague of Alonzo Church, called Haskell Curry, though it is not Curry's greatest accomplishment. So let's figure out what currying is using an even simpler example related to one we saw before. So imagine, currying, that sort of implies that this is a verb or this is a procedure. And in fact, it is. So imagine we have this box called curry. And I want to do something like our add n example, but I want to do it sort of generically. So in other words, curry is to that process what sum was to some int and some squares. So I'm going to think about how to do that. And I want curry to take a plus and a 2 and return a function that I might call add 2. And similarly, I might imagine taking the box curry and put in star for multiplication and 2 and getting out a function called double. One more, I can imagine taking multiplication and 3 and putting them into the curry box and getting out a function called triple. So far so good. We can think about this in general. And of course, in scheme, we can imagine doing this in some kind of fashion. We could say, I'll just write a couple of these. We could say, define, I'll just do the last two. Well, do all of them. Define add 2 to be curry plus and 2. I could say define double to be curry of times and 2. And I could define triple to be curry of times and 3. And I could use them just as before. I could say add 2 applied to 3, and I'd get 5. I could say double 3, and I would get 6. And I would get apply triple to 4, and I would get 12. And of course, all this will be done within the substitution model. So at this point, I'd like to challenge you to write curry, and you can also, I'll also give you the answers on the web, or you can ask us. But how would you write this higher order procedure curry? You won't be able to do it, in class. I'm thinking this might take some thought. And if you can write curry, well, let's sort of start out what curry might look like. And then I want to tell you kind of what you've done mathematically. So if you wanted to write this curry function, as I've done it, you might imagine doing something like this. So again, we have the same idiom, define curry, which is a procedure. How do we make a procedure? Lambda, f, and some value x0. So in this case over here, let's take the triple. F is obviously the multiplication function, and x0 would be the 3, the fixed value of x. And then we want to return a function of the other parameter, let's call it y. And then the question is, what should be in here, in this box? So this is your problem. So once you figure this out, let me tell you what we're really doing mathematically. And it's a little peek into why there's this beautiful confluence of mathematics and functional programming. So that's the computer science view up top. Here's the mathematics view. So suppose we have some function. We have a function like f, and it takes 2 arguments. And over here, we have functions like plus and times. But suppose for the sake of argument, they could take different types even. That the function f, the first argument is of type x, and the second argument is type y, and I'll say cross here. So it takes one from column A, one from column B. So one from x and one from y, and it returns something of type z. So this is how we'll denote, we'll be quite a bit more formal about this later. This is how we denote that we're interested in a function that takes 2 arguments, the first one being of type x, the second being of type y, and they return something that must be of type z. And suppose furthermore, we have a fixed point, say x0, that's at x. So to reify this assumption a little bit, what we are going to have in these cases, f is either plus or times, and in all cases, x0 is going to be 3, or x0 is going to be 2, as in this case here. So an example of x0 would be 2 or 3. An example of f would be a binary operator like plus or times. Now suppose we've written Curry successfully, filled in the box, and we say let a function g be the result of applying Curry to f and x0. Then one way of characterizing g is that g is a function that takes something of type y as input and returns something of type z, where g of y is mathematically defined to be f of x, 0, and y. So the way I like to think about this is that the coding problem of going from here to here is certainly doable. And of course, you'd probably look at these examples too. Certainly doable in some sense. And that's what sort of being a good programmer is all about, because this is sort of a specification. But once we're comfortable with the language of functions and sets, so here we have functions, here we have sets and so forth, this gives us a description that makes it substantially more straightforward to fill in this box. So I don't expect you to be able to do this right away, but try it and think about it. To make this not too intimidating, the answers are actually already on the web, so you can look at how Curry is implemented in the scheme. It has a very simple solution. And one other thing I'll say, and this is a paid commercial advertisement, is that a couple of years ago, I had a very ambitious TA who wanted to implement Curry in other languages. And he came up with about 180 lines of C++ code that would implement it that way in certain cases where it usually didn't break. So you can sort of see the referential transparency and the elegance of scheme and expressing mathematical ideas, the fact that we can do this really very compactly, and also using just the material that we've used so far. So in summary, in order to get from where we are now, to going further, it's going to be a little bit of a mathematical climb, but we'll help you with each of the steps. And in particular, I think this class is sort of a paradigm for that, because we did not need to learn any new scheme, no special forms, no new syntax, no anything. We just got to use them in ways, layer them on top of each other. And what we could do is we could basically do mathematical summation. So now we have at least finite series. Later we'll have infinite series. We could do integration. We could do differentiation, so a good part of calculus. And we could even look at these more abstract objects, like repeatedly effing its object to get a iterated or repeated function application. And even this example of Curry, which is something that turns a 2-argument function into a 1-argument function. So I would say that there are some cool things that you can look at, and you can ask us for help. Try to solve this problem by induction, prove this by induction. Try to write Curry without looking at the notes, and see if you can write this. And if you get stuck, you can ask us, you can look at the notes. And with that having been said, I think what I'd like to do is to close the class, maybe a couple of minutes early even, and I will stay and answer questions from you all. I'm happy to do that. So I'm going to stop the recording now. And if you'd like to stay and talk to me either till the end of the class or beyond, I am happy to do that. So where's my recording button? I'm going to stop the sharing. And I'm going to pause recording.